Good evening. This video is to cover two learning targets. The first one is to be able to identify elements and compounds using chemical formulas, and the second one is to be able to identify states of matter using symbols. Those two learning targets that we introduced in Unit 3. So, let's see what we got going on here. Little review to start. Recall an element is defined as a substance with one type of atom. So for example, we have zinc. That's the stuff we coated those copper pennies with in the Philosopher's Stone lab. We model this by having a sample with just one type of atom. These ones are denoted with the little blue circles. And here's an actual picture of zinc down here like that. And this is also considered an element because hydrogen gas, we call it a diatomic, because you have two hydrogen atoms that are bonded together, and because they are the same types of atoms, we still consider it an element. So here's the model that would describe hydrogen gas, where you've got two hydrogens bonded on top of each other. And here's a picture of a tank of hydrogen to remind you what hydrogen gas looks like inside of a container. Now here's compounds. Compounds are defined as a substance with two or more types of atoms. So these are going to be different. For example, we have water. And inside of water, we've got two hydrogens and one oxygen. And we can model it like this, where the orange dots are the oxygens and the black dots are the hydrogens. So that would be a model for water. And there's a picture of water like you needed it. There's me flying into the corner. And salt, sodium chloride, table salt. We can model that with one sodium represented by the green and one chlorine represented by the red. I should have flipped the colors. You'll know why a little bit later on. And not that you need to see what salt looks like, but there is a sample of salt crystals down there just like that. So this is a little review of what's the difference between elements and compounds. So another review tip here, every element has its own symbol. There are only 118 known elements in the universe as of this point. We are either synthesizing more elements, or maybe we'll find more elements in the universe someday. And they each have their own corresponding symbol. So here's a great picture of a periodic table here. And here's a little alert. You also see this on Schoology. At this point, make sure you have a plan to obtain a black and white copy of a periodic table. We're going to need to color code it eventually. Don't color code it according to this one, because we're going to color code it in a particular way. Look at Schoology to see where you can find a black and white copy of a periodic table. So here's my periodic table I'm going to use as a sample here. Here's hydrogen we find in water. It has a symbol H. Here's zinc. It has a symbol capital Z, lowercase n. You'll notice that element symbols will always have one capital letter and the next letter will be lowercase. So here's sodium with capital N, lowercase a. And there's chlorine. So sodium and chlorine bonded together make sodium chloride, NaCl. I circled chlorine here because everybody always confuses that second letter as the letter I. It is not. It is a lowercase l, capital C, lowercase l for chlorine. So make sure you come up with a plan to obtain that black and white periodic table and start looking through it. I'm not going to require you to memorize elements on the periodic table, because through the course of using your periodic table so often, you accidentally memorize it. So there's our element symbols. Now let's take a look on how we can tell how many and what types of atoms are contained in compounds by looking at their chemical formula. So let's take hydrogen gas, for instance. Remember, there's our model of hydrogen gas. These are two hydrogen atoms bonded together. That's why they overlap. And the formula is H with a subscript 2, because each of the molecules consists of 2 hydrogens. Here's another example. Here's water. There's our model for water with 1 oxygen and 2 hydrogens. The formula for water is H2O, where 2 here is the subscript, because every water contains 2 hydrogens and 1 oxygen. Here's the big moral of the story and the big takeaway with this. The subscripts in the formula tell you the number of atoms or ions that are present inside of the substance. So we're always looking for the subscripts to tell us how many of each type of atom or ion are present. Okay, so let's take a look at an example here. Here's copper sulfate. Copper sulfate are these beautiful blue crystals. You find copper sulfate sometimes in the fertilizer section, in the garden section at like Home Depot or Lowe's. It can be used as fertilizer. It can be used for all sorts of different stuff as well. We use it a lot in chemistry because it's a great chemical to use to teach chemical reactions. So my question is, how many of each type of atom are in 1 molecule of copper sulfate? And here's my formula just like this. So I'm going to look at what types of atoms are present first. And I see I've got a capital C, a lowercase u, and I can find on my periodic table, this is number 29, and it's copper. I can also see I've got a capital S. I'm always looking for the capital letters in these. So I got capital S, and I've got capital O. Now you notice here that there's no subscript by the copper or the sulfur. There's no subscript here. When there's no subscript, we pretend that it's a 1. So that means in copper sulfate, I've got 1 copper, 1 sulfur, and you'll notice by the oxygen, there's a subscript 4. That means that I've got 4 oxygens present. So to make a model of this, and this is just to kind of show you what it would kind of look like here. A copper sulfate molecule would have 1 copper, 1 S, and 4 O's. And you don't know the reason I'm putting them this way around here. I'm just doing this as a visual for you to kind of see right now. But that is kind of how 1 molecule of copper sulfate would look like. We'll refine that at a later date. Moral of the story, I'm always looking for the subscripts to tell me how many of each type of atom there are. And I'm looking for a capital letter to indicate that I've got a different type of atom. And if it's a lowercase right next to it, it's probably an element on the periodic table with 2 letters. Okay, here's our next example. So we got ammonium nitrate. The formula for ammonium nitrate is NH4NO3. We will learn later how to name these different types of compounds, but for now, just trust me that the formula is NH4NO3. So how many atoms and what types of atoms do we have in each one of these molecules? So I'm going to look for the different types of atoms to start. And I'll notice here that I actually have 2 N's in 2 different locations. As of this point, you don't know why, but they're the same N's. They stand for nitrogen. So I'm going to just write 1 N because they're just repetitive. Then the next capital letter here I've got is an H for hydrogen. Then I've got an O for oxygen. So sometimes there's more than one type of atom, even though there's no subscripts. I've got a 1 here and a 1 here. So 1 nitrogen plus 1 nitrogen makes 2 nitrogens. And I've got 4 hydrogens. And I've got 3 oxygens. So the answer here would be I've got 2 nitrogens, 4 hydrogens, and 3 oxygens in ammonium nitrate. And just to model this, you don't know why I'm drawing it the way I'm drawing it right now, but just to model this, to imagine 1 molecule of ammonium nitrate, it would look like something like this, where this is all one big bonded blob of atoms. So every molecule of ammonium nitrate would have 4 hydrogens, 2 nitrogens, and 3 oxygens. All right. So let's look at a different type of compound and how to count the number of atoms in that one. Okay, so here we've got groups of elements and compounds. Okay, so let's look at different types of groupings of elements and compounds. Some compounds, there can be 2 different types of bondings. And even if you don't know what those types of bondings are as of yet, we'll learn about them. But when we want to distinguish between those 2 different types of bondings, we put some of the elements in parentheses because they make up their own different type of compound. And the parts of the compound found in parentheses have a name, and that name is called polyatomic. Poly means many, atomic means atoms. So if I have many atoms in parentheses, it's called a polyatomic. So let's look at an example here. Here we've got Cu with an NO3 in parentheses, and outside the parentheses, I've got the subscript 2. I'm going to start this one with a model so you can see what it would look like. And then we will count the types of atoms and the number of each type of atom. So this is what copper nitrate CuNO32 would look like. I've got a copper, I've got 2 nitrogens, and I've got 6 oxygens. Of course, this is not on the subatomic level how this really looks, but I wanted just to show you how I would count these things out. So inside copper nitrate, I'd have 1 copper, 2 nitrogens, 1, 2, 3, 4, 5, 6 oxygens. And to do this without drawing it out, I first go back and look for capitalized letters like I did before. And I've got copper here with no subscript, which really means 1. So it's 1 copper. And look what I did with this 2 that's outside of the parentheses. You might remember the distributive property in math class. Don't stress that I said the word math. It's simple math. But what I can do here is I can distribute that 2 to everything inside the parentheses. So this means that inside the parentheses, I've got 1 nitrogen, but outside the parentheses, I got 2 of these NO3s. 2 times 1 makes 2 nitrogens. I got 3 oxygens inside the parentheses, and I have 2 sets of NO3s. That means I've got 3 times 2 to make 6 oxygens. So the answer here would be in a molecule of copper nitrate, I would have 1 copper, 1 copper. I'd have 2 nitrogens because I distributed the 2 to the inside, 1, 2, and I would have 6 oxygens because I have 2 groups of 3. So 3 times 2 makes 6 oxygens. 1, 2, 3, 4, 5, 6 oxygens. So let's look at another example here. This is a little bit more complicated. This one we call ammonium phosphate. You don't know why it's called ammonium phosphate yet, but it is. And I've got 2 sets of polyatomics. First thing that I do, just like I did in all the other problems, is I'm going to look for the different types of elements contained in the ammonium phosphate. I've got some N's. I've got some H's, so I've got some nitrogen and some hydrogen. I've got some P's, or AP, as you will see, and I've got an O. So I've got 4 different types of atoms in here. I've got nitrogen, hydrogen, phosphorus, and oxygen. And you can correlate the names of the symbols on your periodic table. So I'm going to do the distributive property here because I have 3 groups of NH4. Pretend that's a 1 there. So I got 3 times 1 makes 3 nitrogens. And I've got a whole ton of hydrogens here. I got 3 times 4. 3 times 4 makes 12 hydrogens. Now, this one here has no subscript on the outside, so I treat that as a 1 as well. So I've got 1 times 1 makes 1 phosphorus, and I've got 1 times 4 makes 4 oxygens. So the answer here for ammonium phosphate is in every molecule of ammonium phosphate, I've got 3 nitrogens, 12 hydrogens, 1 phosphorus, and 4 oxygens. You're going to see your Edpuzzle pop up a question here with one more practice to see if you can nail down the correct answer for what type and how many of each type of atom is inside a molecule of particular compounds. All right, one more way that we can denote how many atoms are inside of a particular compound, and not only that, how many molecules do we have? So I'm going to ask you this question. Your Edpuzzle is going to stop for a second and you're going to answer this question. But what do you think the 5 in front of this H2O means? What do you think that 5 means? So it's going to pause, ask you that question, and see if you're right in a second. All right. So what does that 5 mean, you think? Well, kind of just like math class, the 5 represents how many molecules are present. So in this case, the 5 out front of the H2O means I've got a total of 5 water molecules. And so if I was to draw this out, what would end up happening here is I would look like this. And you will not know yet why I'm drawing water in kind of this bird shape, which what I call the bird shape of the water molecule. But I'm modeling this out to you to show you that 5 in front of the formula H2O means you've got 5 water molecules. So it's just multiplying however many molecules you have by the number on the outside. Now, if I was to ask you how many of each type of atom here, well, I would distribute again, but I distribute the coefficient to the subscript. So in this case, I got 5 times 2 makes 10 hydrogens. And I've got 5 times 1, which would make 5 oxygens. So if I have 5 water molecules, I've got 10 hydrogens and 5 oxygens. And that's how I can tell how many molecules I've got. I'm going to give you another practice problem on your Edpuzzle, and then you're going to move on to your last learning target. So your last learning target on this video covers how can we tell the states of matter by using symbols. So remember states of matter, solid, liquid, gas, and then I'm going to introduce maybe a new one here called aqueous. I'll explain what that is in a moment. But let's look at an example here. So one question you might be asked is what's the difference between NaOH solid and NaOH aqueous? Well, each one of these contains 1 sodium, 1 oxygen, 1 hydrogen. Looking at the capital N lowercase a, that means it's its own symbol, sodium. So you have 3 different types of atoms here, sodium, oxygen, hydrogen. And I got this little s in parentheses here and this little AQ in parentheses here. Well, you might have already guessed that the little lowercase s in parentheses will mean that that is in a solid state of matter. So NaOH with the subscript lowercase s in parentheses means you got a solid. Now, what do you think the AQ means? Well, this sodium hydroxide, this NaOH, dissolves incredibly readily in water. So if I dissolve this in water, I now have a homogeneous mixture, or otherwise known as a solution. So here is sodium hydroxide solution. It's pink because we put this indicator in it to turn it pink, and we'll do that a little bit later on in chemistry. And because the solid sodium hydroxide is dissolved in water and you can't tell the difference between the two phases, we call it aqueous. So that is NaOH, aqueous. Anything that is dissolved in water is called an aqueous state of matter. Here's a point that you should write down a couple of notes, because here are your state of matter symbols. They're pretty intuitive here. Lowercase s, and it's always a subscript. Lowercase s is solid. Lowercase l is a liquid, and it is not the same lowercase l that you will find by the capital C in chlorine. This one is going to be the lowercase l by itself, which means liquid. And then lowercase g is going to be a gas. And then the lowercase AQ means a homogeneous mixture of a solid and a liquid, and the liquid is most of the time water, but it doesn't have to be, but most of the time it's going to be water. Please take a moment to write down these state of matter symbols somewhere where you will remember them. This is the end of the translating formulas into number and types of atoms video. You're going to find at the end of this video, there's going to be a couple more questions attached to your Ed puzzle for review. You're going to have a voluntary practice worksheet to get good at telling what types and how many of each type of atom you have in compounds. It's completely voluntary because you're going to practice this stuff to get good at it enough to take the little assessment that you're going to find on Schoology. So if you have any questions, please don't hesitate to contact me and ask. Thank you for your attention. Hopefully this was clear. Have a good night.